Hello. Thank you. This is my seminar. So, yes, pants off. Someone sounds Scandinavian. Okay, so let's talk about 4K music. First of all, audio data is huge. This stuff runs at like 44,100 hertz. So yeah, that's a lot. 4Ks are tiny. This is a problem. We need to fit music in a very, very small space. Obviously we can't store audio, we have to generate everything. So that's what synthesizers are all about. That's our solution to the music in 4K problem. So I'd like to show a couple intros, just so you can kind of get an idea of what current 4Ks sound like. Yeah. Yes, they take a very long time to pre-calculate because of the music, and I'll get to that later. Very long time. Yes. This is state of the art here. You're free to go get a drink.
Brock says that state of the art didn't have to pre-calc.
Yeah. Oh well. Yeah, we'll drop this intro. That's taking way too long. Oh, there it goes. Of course. Yeah. Oh, I'll do the next one. This next one I actually know will work. The other one is mine, by the way. You can see how good of a coder I am. Show us yours. Yes. Oh, look at that. All right. So those are the 4Ks I wanted you to see. Now that you know what a 4K synth sounds like, let's talk about how they work. Okay, so the basic concepts of a synthesizer and making music in general, on computers at least. So you have buffers and samples, and if you know how to code, you know what a buffer is. It's just a big array. So samples, yeah, each slot in this array is a sample, which actually represents the position of your speaker in terms of the electromagnet in the speaker box. So like, yeah, you have 0 and negative 32K and positive 32K, and the speaker will move depending on what you give it. You can think of it like pixels, but for sound, like how multiple pixels come together to represent an image. Yeah. Works the same way with sound. So sound is originally made with oscillators. This is pretty basic for you music guys. Oscillators just a periodic function, goes over and over again. You change the pitch, or you change how fast or how slow this repeats, and you get different notes. Filters will take input and do things like low pass, which cuts out all the high frequencies, or high pass, which is the opposite. And then what they do is they just basically shape the sound. They take what came from an oscillator and make it more interesting and bearable to listen to. And then envelopes will control the volume of a note. So like if you hit a note, what happens is you don't just have sound and then you're done. Well, you can. Chip music usually works like this. But yeah, you actually have the volume ramp up a little and then play a little while and then ramp down, or more complicated envelope structures. So yeah, envelopes just eliminate clicks and pops at the beginning of a sound, because if you imagine with the speaker position thing, if you don't have an envelope, all of a sudden your speaker has to pop to one position and then start oscillating, and that you actually hear that as a pop, because it's a sudden change in air pressure. So, rendering pipeline of a standard synth. Oscillators, you have a bunch of, like a buffer for each instrument. So the oscillators for that instrument will just fill it with sound. then the filters will go over this buffer, just pretty basic code here, and just go through and do basic transformations on the waveforms. After that, mixers will combine the buffers, and these don't actually have to be in order, because after you've combined these buffers, you can put these in more filters and do more things and things like that. So then you convert the final buffer to a different output format, usually different bit depth, things like that, and then send it elsewhere to be played. That's a standard rendering pipeline in 4K. So I'd like to give you an example of a synth. This is my synth tool that I've used for a couple years now, and I don't like it anymore, but it works. Let me pull this up. Yeah. Oh, look at that. The resolution is great. That's okay. So this is my synth. Yeah, you basically have this grid setup. If you've ever seen Workzoid, which is Farbrush's 64K tool, or Klangzoid, which is Gargai's 4K synth, it's all the same concept. This represents workflow. So to make a sound, you'd say you make an oscillator here. And I guess there's a resolution here. I'm going to have to make a few. Oops. And route all these like that. So now one of these will play notes. Yeah. Yeah. So that's the basic building blocks of my synth. You have just what I described, which is you have the oscillators, and if you could see more of this, you could see they have just parameters like which note they should play, their volume, and things like that. You can also see there's the different waveforms here that these are generating. That's the difference between like a square and what before you heard was a sine. And you'll notice they sound extremely raw and actually pretty unpleasant. So I'll play them more, just to make you suffer. So that's what filters are actually for. So if we put a filter in this mix here, now this oscillator that we have notes going through goes through the filter to the mixer, to this mixer, to the output. And yeah, I just have these oscillators because their columns are to the left here and screen resolution is terrible. So in this case, if we have a low pass, for instance, we turn the what up? Okay, dry is not going to go down. Not going to go down. Okay. Yeah, I can't really turn the dry signal down on this, but what basically happens when you put a signal through a low pass is it kind of goes like if you have a tone that sounds like ee, then it goes ooh, and I don't know. It's kind of hard to explain, but yeah, that's what filters are for. So the cool thing about this synth, well, I'll get back to this. Yeah. So the good thing about this synth here is that it has a modular design, which means you don't just have a set way that your signals go together. You can take signals and split them and mix them again and filter different things differently. And that's really important, especially in 4K, because you have these extremely basic waveforms and you can't really do much out of them. So you want to be able to filter them and route them as creatively as possible to get the most advantage out of them. It's also analog modeled, which means it had those basic waveforms. There's other things like FM synthesis, which is where you have a signal frequency and a carrier frequency. And basically what happens is, or a carrier and a modulator. And one frequency will go up and down, like a normal oscillator, and the other one will actually change its pitch or different parameters extremely quickly, and it makes a different tonal quality. But yeah, I think the group Loonies uses a synth like that. But mine, along with the synth from TBC, use analog modeling, which is pretty basic. And it's also what all the hip kids are into these days, so that works out. My synth also has a filter with a sine LFO. If I could have showed you more about the filter, I could have explained this better, but an LFO stands for low frequency oscillator, and just like an oscillator that would make a pitch is really fast, an LFO it just is the same thing but slower. And instead of actually routing it to the speakers to hear it, you route it to a parameter to change it over time. So like in the case of a filter, we would change the cutoff, and the sound would kind of do a wow 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 kind of sound. That's pretty standard to synths. So, yeah, that's why that's useful. The other thing is a tracker interface. One of the hard things about making music tools for size-limited intros is you have to be really careful with the way you design your tools, because musicians are terrible to work with, always. And so you have to basically make your tool for them. And I got lucky because I also do music in my group, so I just went with a tracker instead of maybe a sequencer-like interface. But all that means, if you don't know what that is you just have a bunch of columns, and each column represents an instrument, and then you play your notes in a top-down fashion, rather than a sequencer, which is left-right, and you can usually control note length and things like that. And yeah, the tool performs basic code generation. So when you make a song in the synth and you save it to use in the intro, what you actually get out of it is an include file for an assembly module that I have that builds the synth with the music later. And yeah, I'll show you what that looks like a little bit later too. So a little bit more on the technical side. When I'm working on the separate buffers, I use floating point buffers, and the reason for this is, well, I mean, it's huge in memory, but that doesn't matter, it's 4K. And you're doing this in pre-calc. The main advantage is that you get a decent amount of quality, and you don't have to bother using any weird arithmetic commands when you have an oscillator, because x86 processors have sine and cosine and things built in, and you can exploit those. For the API, so when I actually generate my wave and I send it off to be played, I just use the wave out API, which is like 3 API calls, and you give it a pointer to your buffer and a size, and it copies the buffer and then begins streaming. So you don't have to handle anything about playing if you pre-calculate your music. Real-time synthesis is much more intensive, I guess. But you don't really worry about that unless you're at the 64K level. Yeah, so the generation, it's all pre-calculated. That's why the intros take so long to start up, and sometimes don't run at all. So yeah, the oscillators, they're pretty basic, just the sawtooth, the sine, square, and then triangle. And there's also white noise. And white noise is useful in mainly the context of drums, which is unfortunate because the noise oscillator is kind of large. Yeah, and also one word is detune. A really cheap way to get really nice sounds that people figured out pretty early on in sound synthesis is if you take two notes that are the same waveform. If you play them at the same pitch, all you get is the waveform stacks on top of each other and it just increases in volume, and that's not very interesting. But if one of them is slightly detuned, just a tiny bit above pitch, then what happens is the crests and troughs of the waveform sort of start to blend together, and you get very interesting sounds. So detune is extremely important. You don't want to just be able to play a note, you also want to be able to play a note a few, maybe half a semitone above. So, when you're building a synth, you need to design with your musician. As I said, musicians are extremely hard to work with. I went the route where I just made my own self-inclusive tool, and some people do like that, but most musicians don't because they have a tool that they usually work in all the time. And so a lot of synths like Forklang, which is publicly available and highly recommended, it's a good synth. Forklang is implemented as a VST plugin, so a musician can use the tools that they already use for music production and just import the synth and work on it that way. So that's really good to check out. The other thing is start simple. I mean, yeah, wish I could have shown you more about what my synth actually sounds like, but the thing is that this synth was my 5th attempt at coding a 4K synth. And so by now I've kind of figured out how it works, but at first I just did really weird stuff that just didn't work. It's a lot of trial and error when you're building something like this, because especially if you were like me where you didn't know much about how sound is actually made and how it works, it's a big learning process and you need to make a lot of mistakes. Okay, so you always need to think small. This is like everything on the 4K level and below. Not as much with 64K. With 64K, it's more like, well, you kind of just write your engine to generate everything instead of actually writing it to be extremely small. 4Ks are different, where you have to squeeze every byte out of every routine that you have. And so you want to be thinking from the get-go, how can I design this to be as small as possible? So one of the ways is that you use either less data or more redundant data. Redundant data is good because it packs well. I mean, in a lot of cases with 4Ks, you'll end up with a bigger original data set that packs smaller than a smaller original data set with more entropy. But that's another topic. You also want adaptable code with preprocessors. So this is actually the only reason that I used code generation in my synth. The synth module, when I compile it, has a lot of preprocessor macros in it. So let's say you write a song and it only uses 3 out of the 4 oscillators. You don't want that other oscillator code in your synth. That just is wasting space. So the preprocessor will take that out for you. Just things like that. Yeah, some more tips on staying small. You need to throw out everything you do not need. This includes quite a lot of things actually, namely the C runtime library. You don't need that, especially with inline ASM and things like that. Avoid unnecessary loops. Usually, well, this is actually debatable because a lot of times loop setup from a compiler is quite large, much larger than you need it to be, and yeah, sometimes it's actually smaller if you just repeat a piece of code a few times with slightly different, slightly different stuff than it is to actually put it in a loop and do it that way. Other cases that's not true, so yeah, it's just something you have to play with at 4K. Yeah, another tip, this is weird. When you're writing 4K stuff with a compiler, when you're not doing everything in assembly, you have to be able to just try weird things, like when I was playing with my loops and I changed all my for loops to do while loops, and they turned out all of them to be 3 or 4 bytes smaller each. And it's just weird stuff like that you can't really predict what the compiler is going to do or how the compressor is going to handle that code. So you just need to be able to try things. Yeah, assembly and inline assembly. If you don't know assembly and you're doing 4Ks, you should probably learn at least a little bit. Even for basic stuff like replacing the sine function, it's like 3 lines of assembly that's easy to learn. And it's extremely valuable because when you're at this level, you want to be able to control every single byte that goes into your production. And this allows you to do that. That's another one of the reasons why I have a self-inclusive tool, is I know all the data that's going through at all times, at all parts of my tool. So I know everything that's happening. Allows me to have more control. Also, disregard rendering speed. It's quite common for 4Ks now to take 30 seconds to a few minutes when they're generating the music in the beginning. Actually, a notable exception to this is Forclang actually will set up the rendering to happen on a separate thread as it's still streaming from the same buffer. So I'm actually shocked that it works so well, but basically the music is just a few samples ahead of where you are when you're playing. So it skips the precalc because it's calculating while your intro is running. You also want to test compression often. Crinkler has a report feature, which is extremely valuable. For those of you that don't know, Crinkler is the ad hoc, or not ad hoc, go-to 4K compressor these days. Yeah, it has a report feature which will generate HTML report of code, and I would really like to show this, because this is really awesome. Oops, there it is. Crinkler out. Yes. This is a compression report. So the nice thing about this is it gives you this pretty little rainbow looking thing. Yeah, but it has all the sections of your code in the way that it's broken down, and it also has compression ratios for each one of these sections. Even better than that, if you go deeper down, you can see your code and byte by byte how it compressed. And this is an extremely good tool because, yeah, like this instruction's big. Yeah, things like that. So you want to be, when you're writing a synth or anything in 4K, you really want to be be always compressing, compress all the time. Every little change that you make, you should recompress and see how it actually affected your compression ratio. Yep, simplify and reuse. A lot of things when you're writing synthesizers can be reused, especially when you're doing 4Ks. There's a lot of graphic routines that are quite similar. Like, good example. Well, yeah, texture generation routines. The noise function, for instance, if you're generating textures and you need like a Perlin FBM construction or something, that can actually be really good for making harmonic noise. And so it's really nice to be able to reuse those kind of routines. More toward the 64K level, it's probably possible to do parameter automation in 4K. Actually, I think 4Klang allows that. But if you were doing splines, for instance, splines are very valuable. If you have a camera spline, why don't you also use that spline system to modulate panning, for instance, like where the sound is in the left-right spectrum. So, yeah. So that's kind of what's standard these days, what's going on. I'd like to actually talk about a new synth that I'm developing with Duckers of Outtracks. And the reason why I want to talk about this is because we're kind of trying to take more of a new approach. And some of it's going really well and some of it isn't. And so I'd like to share some of this process. So first thing to know is it's virtual machine based. And if you don't know what a virtual machine is, it's essentially an emulator for a computer that doesn't exist. Like if it takes in bytecode and then interprets it a different way. The most notable virtual machine that you definitely have heard of is Java. That's why Java runs cross-platform, because there are multiple machine backends that will actually take in the Java bytecode and do what it's supposed to do. So yeah, so we chose the same design style for our synth. The original plan was to just write a virtual machine with basic operators like a sine and add and things like that. So then we were going to write the synthesizer in the assembly language of this bytecode. And yeah, while that was cool, we figured actually we could do a much more open approach. So we actually made everything extremely atomic. We still have the same backend, but instead of writing the synth in that, we actually expose that in our tool. And I'll show that in a second. It's horrible to use, but that's one of the things that we're working on that, yeah, it'll make more sense so you can see it. Also, it's tiny. Most 4K synth cores are around 500 to 600 bytes, depending on what features of the synth you use. We haven't gone up to 300 bytes yet, so we're doing well. Yeah, so this is what the tool looks like so far. It's pretty basic. Let me just open something I threw together earlier. Yeah. My master is somewhere around here. There it is. Okay, yeah, so this tool is done in C# with .NET. Yeah, the tool's not really very important. But the thing is that you see more here. Okay, so how the tool works, and yeah, how this is each one of these devices actually represents one of the instructions that we have in our virtual machine. So like mix, for instance, represents add. You have 2 inputs, 1 output, basic stack machine. Yeah, inputs, outputs. Yeah, we have a filter opcode, things like that. Yeah, saw, osc, and frequency. Yeah, so what this tool actually does when you create a graph like this, and this is why it's so terrible to use, is because it takes quite a lot to not get very good sound. Let me just play this little loop. Yeah, really basic. And yeah, that's this main synth. So we have the master here, left and right. So we take a track, which takes in these notes, pass that to the screamer, which is the synth, and then multiply it to bring up the volume, and then out of the master. So in this synth, yeah, you basically have to wire up everything. So what the tool does is it's a graph compiler. So it starts at the end here and works its way up and compiles just like any programming language would. So this gets converted into bytecode, which looks like this. We have a disassembly window which shows what our bytecode looks like. So this code, which as you can see would be very small because each of these is about 1 byte, less when it's compressed. And yeah, that makes what you heard. Yeah, so that's our current approach. But the major problem is that when we're actually using this and trying to make anything interesting, it's a lot of work to get very basic sound. This synth that I played wasn't very interesting. It's basically, yeah, here's a saw, and then a couple detuned saws on top of it, which is called a super saw, which is just a bunch of detuned saws put together. And then, oh, I have an LFO on this. Figure this. That'll work better. Yeah, that's what LFO does. So, yeah, that's what we're currently working on. Yeah, so actually, that's all I have. Here are some resources. I'll leave those up after the seminar, I guess, so you can take those down. So yeah, any questions or comments? Yeah?
How big is because you say bytecode is very short.
Yeah.
But when you say 300 bytes, is that excluding computation?
Yeah, that is the virtual machine.
So you have 300 bytes virtual machine, and then you have...
And then you have the music data on top of that, yes. Still, we haven't gone over around 500, 600 bytes for decent stuff, but it's so hard to work with that we haven't done anything with it. One of the approaches that we're actually thinking of doing is writing a C-like language compiler for this virtual machine, so that way I can just write the instruments that way, because it's essentially the same representation as the graph format, but easier for me to understand at least.
It reminds me of the way you work in reactor.
Working what?
It's like,
I don't know what.
okay, it's a similar concept essentially, but it's a big package.
Okay, cool. Yeah, the virtual machine approach is usually good for quite a lot of things, actually. It's really versatile, good thing to know. So yeah, well, thank you guys for listening. Have any more questions or just want to chat? Feel free to let me know, even if I have my headphones on. I'm not a jerk, I won't bite. So yeah, thank you.